All right, so we are going to talk about current electricity today, and our objective is to be able to describe how electrons flow in a wire. So we've talked about potential difference when we were in electrostatics, but now we're going to revisit it for current electricity. It's the same thing, but I'm just going to go over it a little bit again, just to remind you of how things work. So let's look at gravitational fields as a way to create an analogy for potential difference. So in a gravitational field, if you lift a 1 kilogram mass 10 meters, the potential energy changes by 100 joules because it's just that 10 meters, the height times 9.81, the acceleration due to gravity times the mass, which is 1 kilogram. For a 5 kilogram mass, it changes by 500 joules. So it's the same process, the same equation. It's just a 5 kilogram mass rather than a 1 kilogram mass. So then we want to know what the work per mass is, and it's going to be the 100 joules divided by 1 kilogram. So it's 100 joules per kilogram. For the 5 kilogram ball, it's going to be 500 joules divided by 5 kilograms, or still 100 joules per kilogram. Lifting a mass against that gravitational field gives it a potential energy. The amount that it falls will give the difference in potential energy. So it had that 100 joules. When it goes down to 0, it's a change in potential energy. It changed by 100 joules. So in an electric field, it works similarly. In order to lift an electron against the field, it takes work. So here we have a positive particle right here, and it's going against the electric field. So it's being pushed toward the positive here, and that takes work. The amount that it falls when you let go or turn the current off or whatever is the difference in the potential energy. The potential difference per charge is called the voltage. So instead of work per mass, we use work per charge. So it's just voltage is equal to work divided by the Q, which is charge. In terms of coulombs, its voltage is equal to joules per coulombs. That's the units. If you're just dealing with electrons, it's going to be a joule per electron, and then it becomes an electron volt, so you don't have to convert necessarily. 1 electron volt is equal to 1 joule per electron, but it's expressed in terms of coulombs. So 1 joule divided by 1.6 times 10 to the negative 19th is equal to a electron volt. But a volt is 1 joule per electron. So 1 joule divided by the 1.6 times 10 to the negative 19th coulombs. So there's 2 different ways to measure voltage. So potential difference in volts. A volt is more formally called the potential difference, and it's measured. It measures how much work it takes to lift a charge, as we saw in the last picture. It's kind of like how hard it is to pull on an object attached to a spring. When the spring's released, the energy will be released as well. So when you lift the charge, you store the energy, and then when it's allowed to drop, the energy is released. You measure it with a voltmeter. So how much work to charge a battery? So if you have 1 coulomb of charge, you can find out how much work it's going to be using the equation V equals work divided by Q. So work is equal to V times Q if you rearrange it so that you can figure out how much work it takes. So if you have a 12 volt battery and 1 coulomb of charge, it'll take 12 joules of work to charge the battery. For 1 electron of charge, you are going to say it's going to be the same equation. So it's still work is equal to voltage times charge. And it's going to be the work is equal to 12 volts, the same volts here. But the charge is going to be 1 electron of charge. So it's going to be 12 electron volts of work to charge the battery. Okay, so there are 2 different kinds of currents. There's AC and DC. There's the direct current. It's a continuous flow of electrons. It's perfectly similar to water that's flowing through a hose. And the electrons only flow one way. It's usually supplied by a battery, and the potential difference stays constant. So this is what we're actually going to be dealing with through this unit. But there is another type of another type of current, and it's called alternating current. It flows one way and then reverses. The potential difference goes up and down from positive 12 to negative 12 volts, and for domestic electricity, and it happens 60 times a second. That's the frequency. So current is the amount of electrons flowing, and the units are in amperes. The symbol is an I, not an L. This is an I. And so an amp is equal to the charge divided by the time. So it's the change in charge, Q, divided by T, or delta Q divided by T. 1 amp is equal to 1 coulomb per second, which is actually a lot of electrons per second. 1 amp is a lot. It's measured with an ammeter. A charge of 30 coulombs passes through a 24 ohm resistor in 6 seconds. What is the current through the resistor? So charge is equal to 30 coulombs. And the resistor is 24 ohms. We'll discuss ohms in a future video, but this is the unit for resistance, and it happens in 6 seconds. It wants to know what the current is. So current is equal to charge divided by time, delta Q divided by T. So it is 30 divided by 6 seconds, and that's going to be 5 amperes. So in order to have electrons flowing, you have to have a potential difference. So there must be like a pressure to push the electrons along. So you can think of it as a hose that's joined at both ends. If that happens, there won't be any flow of water until a pump is placed within that, we can call it a circuit. So if there's a pump there, then the hose will flow, the water in the hose will flow, and that's the same thing in a electric circuit. You have to have something to cause the electrons to flow, so you have to have a potential difference. In a closed circuit, that's the only way to get that to happen. An open circuit has an opening where the wires are not connected. And in a closed circuit, they are able to go around and around in a loop. We'll talk about circuits more as we go forward. So this is an example of a circuit. So this is what I mean by a closed circuit. You have the positive end of the battery. Conventionally, it goes from positive to negative, so it'll go around, and then it can go around and around. But in the open circuit, it gets here, and it can't make that jump. It's not able to. This is a symbol for a switch, but it means there's a break in the circuit at the moment. If they closed it, then we could keep going around.